Hello everyone, welcome to the channel Top Gate. In this video, I'll discuss one more algorithm of CPU scheduling that is called as a priority scheduling algorithm. Clear? So the priority scheduling algorithm is the algorithm in which with every process one number is associated. That number is called as a priority. Like whenever we are executing some process in a system, so sometimes it happens like few process comes and they have so much priority that at that time we have to leave every other process and execute this high priority process first. Like suppose for example in a system there are several processes going on, and there is one process which is responsible for running the CPU fan. So suppose in some case if the CPU becomes overheated, then this process has to be invoked and this process will execute the CPU fan to cool it down. So suppose if the CPU heats too much, it is overheated, then at that very moment the process which is responsible for running the CPU fan is of highest priority. So at that moment when the CPU becomes overheated, we have to execute that process and every other process which is running in the system has to be stopped right away. So that is a basic concept of the priority scheduling algorithm. So let's discuss this algorithm with the help of these few points, and then I'll give you an example, and with the help of example I'll tell you how we solve the problems which are associated with the priority scheduling algorithm. Clear? So the first point says that the priority scheduling algorithm has two variants. So like we have already studied about the SJF algorithm. SJF algorithm has two variants. One is a preemptive one is a non-preemptive one. So likewise in priority scheduling also we have two variants, that is it can be solved with the help of the non-preemptive approach as well as it can be solved with the help of the preemptive approach. Clear? So that is the first point. Second point says that the priority number is associated with every process. That is, like in the previous examples I gave you, in that one we were given with three things. One is the process ID, second thing is the arrival time, third thing is the burst time. Now in this one, apart from these three values, we'll be given one more value that is called as a priority. So with every process, one priority number will be attached and we have to see that priority number, and based upon that priority number we have to execute every process. Clear? So suppose with every process one number is attached, 1, 2, 3, 4, something like this will be attached, and it will be told to us in advance that whether 1 is highest or 10 is highest. Third point says that CPU is allocated to the process having the highest priority. So whatever number is highest, suppose if 1 is highest and with any process 1 is attached as a priority, so that process is of utmost importance. It has the highest priority and it has to be executed at the very first moment. Clear? Fourth point says in case of tie, FCFS is used. That is, suppose there are two processes who are having the same priority. Suppose 1 and 1. 1 is attached to process P1 also, 1 is attached to process P2 also. So in this case, both the processes are having the same priority. So there is a tie. So if there is a tie, so likewise we did in SJF algorithm, we'll do in this one also. That is, we will use FCFS. That is, whoever process is coming first will be scheduled first in case of a tie in priority. Clear? Fifth point, importance is not given to either AT or BT. AT is the arrival time, BT is the burst time. Now that is the most important thing in this one. Why important? Because when we studied about the FCFS algorithm, so in FCFS algorithm, I told you that the importance was given to the arrival time. We were not concerned with the burst time. Burst time can be anything in that case, but we were most concerned with the arrival time. So that is, if the process is arriving early, then it has the highest priority. That is, it has to be scheduled first. And with the process which is coming later on, it has to be scheduled later on. So that was first come, first serve. Fine. So in that one, we were more concerned with the arrival time. Now the second algorithm was the SJF. So in SJF, we were not concerned with the arrival time. That is, whether the process is coming early or it is coming afterwards. But if its burst time is shorter, we were scheduling that process first. It was a greedy approach. We were only concerned with the burst time. If the burst time is shorter, we have to schedule that process first. But in this algorithm, we will not give priority to either the arrival time or the burst time. whether the process is arriving early or it is arriving late, whether the process is having a shorter burst time or a longer burst time, we do not take care of all these things. We only take care about the priority that is attached with every process. If the process is having the highest priority, it has to be scheduled first. And if we are doing a preemptive approach, then any process which is executing right now and before this process can complete, any other process comes which is of highest priority than this one, then this process has to be stopped and the process with the highest priority has to be scheduled first. Fine. So this is the basic idea of this priority scheduling algorithm. One more thing, if we talk about the FCFS or the SJF or the SRTF algorithm, every process can be called as a priority algorithm, a special case of the priority algorithm. Why? Because if we talk about the FCFS algorithm, then in FCFS, the priority was given to the process who was coming first. So that was a special case of the priority algorithm. If we talk about the SJF algorithm, then that is also a special case of the priority algorithm. Why? Because we are giving the priority to the process who is having the shortest burst time. Fine. So in this one, we are not taking care of the arrival time and the burst time. We'll be only concerned with the priority number that is associated with every process. Clear? So I hope this is a little bit clear to you. So it will be more clear when we discuss this with the help of an example. So let's quickly go to an example, and first example I'll do with the non-preemptive approach, and then we'll move on to the preemptive approach. So let's quickly solve this example, and this algorithm I'll be solving with the help of the non-preemptive priority scheduling technique. And in this one extra thing is given, that is the priority is given here. With every process one priority is attached, and smaller the number, higher the priority, that is the 1 is the highest in this case. It will be given in the question. In some of the questions it can be given that 4 is highest, 1 is lowest. In some of the questions it can be given as 1 is highest and 4 is lowest. So in this case, let's consider that 1 is the highest number and 4 is the lowest number. So as we can see, this process P2 has the highest priority. Fine. And we are doing this problem with the help of the non-preemptive approach. That is, if the process comes onto the CPU, it will not leave the CPU unless and until its work is completed. Clear? So let's quickly make the Gantt chart first, and if we make the Gantt chart correctly, we can calculate all these values very easily. Clear? So currently we are at time 0. So I'll see that at time 0, is there any process which comes in the RAM? So yes, there is P1 which is coming on into the RAM at time 0. So there is only P1, and this P1 is having the priority 3, which is not highest. But since we don't have any competition right now, there is no process in the RAM right now, so we will only schedule P1 right now. So since it's a non-preemptive approach, P1, if it starts at 0, it will complete its whole 3 units. It will not stop in between. Okay, so it will start at 0 and it will complete its work at 3. So this P1 is completed and it will exit the system. It will be terminated. So now P1 does not exist into the system at all. Okay, now we are at time 3. So I'll see till time 3, are there any processes which are arriving? Yes, P2 is there, P3 is there, P4 is there. So P2 is coming at 1, P3 is coming at 2, P4 is coming at 3. So all these 3 processes are there in the RAM, and the competition is between only these 3 processes. So I am not concerned with arrival time or the burst time. I am only concerned with the priority number attached to the processes. So out of 1, 3 and 4, P2 is having the highest priority, because I told you that 1 is the highest priority and 4 is the lowest priority. So out of P2, P3 and P4, P2 is the highest priority. So at time 3, P2 will take over the CPU, and since it is having the highest priority, it will complete its whole 1 unit. So its burst time is 1. So it will start at 3 and complete its work at 4. It will also complete, terminate, and goes out of the system. So now we are at time 4, and I can see that at time 4, P5 has also arrived into the RAM, and now the competition is between P3, P4 and P5, and out of which 3, 4, 2, 2 is the highest number. Therefore now P5 can begin the execution. However, P5 has just come into the system, but since its priority is so high, so therefore P3 and P4 has to wait here. Fine. So P5 will take over the CPU now, and its burst time is 5, so it will start at 4 and complete its work at 9. So it will also complete and terminate and goes out of the system. Clear? So now there are only two processes, P3 and P4, left in the RAM, out of which P3 is having the highest priority of 3. So therefore P3 will start at 9 and its burst time is 2, so it will complete its work at 11, complete its work and go out of the system. Next process is P4. That is the only process left now, so its burst time is 1, so it will start at 11 and complete its work at 12. So it will also complete and terminate and goes out of the system. So this is the Gantt chart for this non-preemptive priority scheduling. So now let's quickly calculate the turnaround time and the wait time. So what is the completion time? So completion time for P1 completes at 3. So I'll write 3 here. P2 completes at 4. I'll write 4 here. P3 completes at 11. I'll write 11. Then P4 at 12 and P5 at 9. So this is the completion time. Now the turnaround time, we know it can be calculated with the help of the completion time minus the arrival time. So I'll quickly write the completion time here, that is 3, 4, 11, 12, 9. Put the minus signs and the arrival times. Arrival times are 0, 1, 2, 3, 4. So I'll quickly write 0, 1, 2, 3, 4. That will give you 3. 4 minus 1 will give you 3 again, 11 minus 2 will give you 9, 12 minus 3 will again give you 9, and 9 minus 4 will give you 5. So this is the turnaround time for the individual processes. Now the wait time we know that can be calculated with the help of turnaround time minus burst time. So I'll quickly write the turnaround time 33995. Put the minus signs and the burst time. Burst times are 3, 1, 2, 1, 5. So 3, 1, 2, 1, 5. That will give you 0. That will give you 2, 7, 8, 0. So this is the wait time for the individual processes. Now let's calculate the average wait time and the average turnaround time. So average wait time is 02780. That is 0 plus 2 plus 7 plus 8 plus 0 divided by the number of processes 1, 2, 3, 4, 5. So I'll put 5 here, and that is 7 plus 2 is 9, 9 plus 8 is 17 divided by 5. That will give you 3.4, and the average turnaround time will be 33995. So 3 plus 3 plus 9 plus 9 plus 5 divided by 5 process, that will give you 3 plus 3 6, 6 plus 9 is 15, 15 plus 9 is 24, 24 plus 5 is 29 divided by 5. That will give you 5.8. So 3.4 is your average waiting time, and 5.8 is your average turnaround time. So I hope this example is clear to you. Thank you so much.